location of these roots depending upon the different values of the damping ratio. So how the location of these roots, it vary in accordance to or with respect to the different values of the damping ratio. So to find out the location of roots, or we can also say that they are known as the poles, let us write first the transfer function of a second order control system. So the expression for the second order, the general expression, how we can generally represent a second order control system, the general expression for the transfer function of second order control system, it is given by Cs by Rs. It is the transfer function, that is Ts, and it is equal to, so this is the generalized expression for the transfer function of a second order control system. You can see that the highest power of S in the denominator, it is 2. So that is why it is known as a second order control system. Now let's find out the factors of this denominator polynomial, because we have to find out the location of roots, or we can say poles, and poles are what? They are also the roots of the denominator polynomial. So let us factorize this denominator polynomial so that we will be able to find out the roots or the poles of this. Now first, let me tell you that this equation, this denominator equation, that is the s square plus 2 del omega ns plus omega n square, when we equate this denominator polynomial to 0, it is called the characteristic equation. Okay, so this is the characteristic equation of a second order control system. Okay, and if we find out the roots of this characteristic equation, we are going to get the poles of the system. Okay, so let's find out its factors. When we factorize it, we will get s plus, this is what we have to convert it into the factorized form. So we will have this s plus del omega n, and this is whole square minus omega n square, and here we will be having del square minus 1. Okay, so this is what s plus del omega n whole square minus omega n square, and multiplication we have under del square minus 1. So this is its factors. Now this has become the formula a square minus b square. So it will be equals to a plus b and a minus b, where this is a and this is b. So let's write it a into a plus b and a minus b form. We will have s plus del omega n plus omega n square. We will have, this is the square form, so b will be omega n under root of del square minus 1. So omega n under root of del square minus 1, and A minus B will be S plus del omega n minus omega n under root of del square minus 1. I hope you have understood it, that it is A and it is B. A is equals to S plus del omega n. We have put it here, plus B. B is what? Omega n under root of del square minus 1. So here we have put A plus B and this is A minus B. Now this equation, as it is equals to 0, so let's equate each of the roots equals to 0 so that we will get the value of S. First, if we equate S plus del omega n plus omega n under root of del square minus 1 equals to 0. And secondly, we will put S plus del omega n minus omega n under root of del square minus 1 equals to 0. Okay, so we have put both the A plus B and A minus B as equals to 0. Now, from here we will get the value of S, that is, suppose it is x1, it will be minus del 1 del omega n and minus omega n under root of del square minus 1. And if we shift it to the right hand side, we will get the second root S2 as minus del omega n plus omega n under root of del square minus 1. This will have here j, okay, that is, it is the imaginary part. So these are the two roots of the characteristic equation. Okay, so we have find out the roots, or we can say the poles. Now we will locate these poles and we will see that how, because you can see that on in both these poles equation we are having the value of del, that is, they are depending upon the damping ratio. Del is what? Damping ratio. So as both the roots they are dependent on this damping ratio, so it will affect, the value of damping ratio will affect the location of these poles. So the roots S1 and S2, they describe the nature of the time response. Okay, this is the first important point, that these roots they are going to describe the nature of the time response. Also you can see that these two roots they are having a real part and an imaginary part. Okay, so the real part of the root, it represents damping. You can see that it is the actual damping which have occurred in the system. So actual damping, it is equals to del omega n. So the real part of the roots, it represents the damping, and imaginary part, it represents the damping frequency. You can see this damping in the imaginary part, we are having omega n multiplied with under root of del square minus 1. So omega n under root of del square minus 1, it is equals to omega d, that is the damping frequency. So this imaginary part, it represents the damping frequency, and real part, it represents the damping. So from these roots we are getting the information about the damping present in a system. That is why we can say that these roots, they describes the nature of the time response, that is whether the system is having undamped oscillations, underdamped, or whether it is overdamped or critically damped. Okay, so roots, they gives us the information about the nature of the time response. Now we have we have got the two roots. Let us now see that how they are located on the S plane. So we will have different values of del. Del is equals to 0, del is less than 1, then del can be equals to 1, and del can be greater than 1, because we know that the value of del, it is in the range from 0 to 1. It can lie between 0 to 1. So we have four values. Del can be equals to 0, it can be less than 1, equals to 1, and greater than 1. So for when del is equals to 0, we know that the system is undamped system. When del is less than 1, it is an underdamped system. And when del is equals to 1, it is critically damped. And when del is greater than 1, it is overdamped system. So we have these four values. Now let us put the value of del equals to 0 in the roots equations. Okay, we were having S1 and S2. So let us put here S1, in this S1 and S2, let us put del equals to 0. So when del is equals to 0, this real part will become 0, and in both these roots, and here also we are having del square, so 0 minus 1, and here we were having also 0 minus 1. So this real part, it has become 0. So these roots are going to contain only the imaginary parts. So when del is equals to 0, the system is undamped and the roots are imaginary, because real part is becoming 0 in it. Now for del less than 1, if you put here del less than 1, it will be negative. Okay, that is, it can be minus 1, minus 0.5. You have to range it between 0 to 1. So it will be minus, it contain here minus sign. So the roots, they will become, they will be having both real and the imaginary parts. So for this system, the roots are complex. Now putting del equals to 1, if you put here del equals to 1, okay, here, so it will be minus omega n minus j omega n, 1 minus 1, it will be 0. It will be 1 minus 1, it is again 0. So the imaginary part is becoming 0. So, and the real parts, if you see real parts, it is also minus omega n and it is also minus omega n. So in both these cases, we are getting minus omega n and minus omega n, the roots values. So when del is equals to 1, the roots are real and equal. Okay, equal, or you can say that they are same. Okay, now putting del greater than 1, let us put here del greater than 1. So it can be 1.2, anything its value, let us try to put here. So if we put here, then roots are again real, but they are different in this case. Okay, because here also we are going to get, it is uh, we are getting this value. So in this part, the roots are real and different. So for these four values of del, we have got the location of roots, that for del equals to 0, the roots are imaginary. For del less than 1, the roots are complex. For del equals to 1, the roots are real and equal. And for del greater than 1, the roots are real, but they are different. So you have to remember these things that whenever you have got the values of del, what will be the location of roots. Now let us plot these roots on the real and the imaginary axis. This is the imaginary axis and this is the real axis. This is positive real axis, this is negative, and it is positive imaginary axis, and it is negative imaginary axis. Here we are having the origin. Okay, now let us plot the roots. Okay, for first we have the, for that is for del equals to 0, the roots are imaginary. Roots are imaginary means they will be plot either here or here. Okay, so if here we are having the value as del equals to 0, that is the system is undamped system. Okay, let's mark it with black. Here we are having the roots. These are poles, so we are representing them by a cross sign. Okay, now we have the second case, that is when del is less than 1, we are having that the roots are complex, that is it is having both real and the imaginary parts. So it will lie somewhere here or here. Okay, so let its value will be here. So this is when del is less than 1, or the system is called an underdamped system. Then we have a critically damped system, that is when del is equals to 1, the roots are real and equal. So real means they will lie on the real axis and they are equal, that is on the same position. So we will have this as the location of the pole or roots. And this is when the del is equals to 1, that a system is critically damped system. Now for the overdamped system, we are having that the roots are real but they are different. Okay, and that is overdamped system. So it will lie somewhat here. And this is the condition when del is greater than 1 or the system is overdamped system. So we have located the poles or the roots depending upon the values of del. What will be the nature of the roots, whether they will be real or they can will be complex. If we join these, they will form a, okay. In this way you can join. It means that they are forming a ellipse on this side. They are joining. Okay. And these are the locations. Let's summarize it, that when del is equals to 0, the roots are imaginary. When del is less than 1, the roots are complex. When the del is equals to 1, the roots are real and equal. And when del is greater than 1, the roots are real but they are different. So this is the location of roots for different values of damping ratio. I hope this video is clear to you. Thank you.